So today, the goal is to talk about this, the last one. But before we talk about the last one, I need to talk about the thing on top. The style is not like, okay, it's not like a method, definition, this, theorem, this, corollary, this is it. No, I try to give a picture to reach this one. So that's the idea. So all the things here are for this one. That's it. Let's talk about why we want this one. Just a recap, what we did yesterday is that we want to do gradient descent, xk plus 1 equal xk minus step size gradient xk. Then we need to know what is this. Then in order to know what it is, then first we need to know what is this. Then to know what is this, we need to know what is this. But this is for one variable, so this is actually for r, but this is n dimension. N dimension is different from one dimension. So we need something else, that's why we need this, and we also need this, and also we need this. So that means this fourth thing actually is for this thing. And because of that, I'm not going to do it like we start linear algebra topology. No, this fourth thing is just for the purpose of the last thing. So they are not the main character. This is the main character. So I'm not going to go absolute full detail on this because this is just review. Okay? The idea is the ultimate goal is we want this so that we can do gradient descent. So then we need to know what is this, right? So therefore we are following. I just tell you the thing we will see later. First of all, we have the directional derivative. Okay. Okay, I don't spell the full thing. We are given what? We are given a function f. Now, this is very general. I just say Rn to Rm. So usually you can say this is a vector space, this is a vector space. But now let's say just Rn and Rm. That means what? This function is not to a scalar. So that means this f is what? Is f1, f2, blah, 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 fm, okay? And the input is n-dimensional variable, so x1, x2, blah, 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 xn. And same x1, x2, blah, 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 xn. And same x1, x2 to xn. Okay, so it's like this. Then now you see this is what? Linear algebra. We don't want to write this long. So we just write, so this is the full f, okay? And then it is the same as, I just write f1, and then I write x vector, okay? In printing, we just write the x this, okay, instead of this. But now I'm writing, so it's impossible for me to do this. So I just draw an arrow. It means vector, okay? So this is what? This is a Rn to Rm function. So what's directional derivative? We are given, number one, we have a function. And then what? We have number two, an x in the domain of f. In this case, the domain of f is Rn. So therefore, x will be just a vector. x1, x2, blah, 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 xn, okay? So it's a vector in n-dimensional space. Okay? Then what? We have 1, 2, and we also have 3. We also given a direction. Okay, direction. In some books, they write D. But because we are going to write so many D, so I better don't write D, I write V. Okay, I forgot. I write V. So what's V? V is also a vector. Okay, V1, V2, blah, 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 Vn. And then also Rn. So that means we are given x and v in Rn. Okay, now let's recap. What's directional derivative? We are given 1, 2, 3. A function, a point, another point. Then what? Then the directional derivative, okay, then the directional derivative is denoted as d along vector v at a function f at x. Some people write df x v. Okay, this is just what they write. Okay, I will use this one. Okay, they are the same as just write equal. It's defined as what? Okay, define is, I put a triangle here, is limit, okay, and then what? Function f, x plus tv minus fx divided by t go to 0 from top. So this is directional derivative. So recap. We have the first thing. What's the first thing? We are given 3 things. A function Rn to Rm, like this. So that means if the function output is a real number, that means m is 1. This is also true. If m is 1, then it's a special case here. This working for any dimension. Number 2, we have a point in the domain. Actually, we have 2 points. Both of them are Rn. That means a domain in f. And then the direction derivative of f at x along vector v is this thing. And this is a very general generalization of what? Of the classical calculus, right? So now let's review what is the classical calculus. R1 to R1, right? And then what's df dx? Is just limit h go to 0, fx plus h minus fx divided by h, right? So now let's say I have R2 to R3. Now we write d along a vector direction v of the f at x. It will be what? Limit h go to 0 plus and then what, f. Now this is a vector, so I will write like this, x1, x2 plus h, and then what, v1, v2 minus f, x1, x2, okay, something like this. The R3 is due to the expression of the f, okay, then this is the same thing. So you can think of this is what, this is the same as, this v is 1, 1, 1, 1. But the idea is when we go to multiple dimension, high dimension, v1, v2 can be different. So that's why we have the freedom here. So that's why we feel, okay, these are standard thing. Okay, nothing fancy. Then what's next? This thing, we also need to talk about, is this limit exist? And then, okay, just revision. Again, we don't go too deep. So limit of something exists is what? For all, okay, the epsilon delta, I mean, for all delta larger than 0, there exists, okay, I forgot the detail, but you know what I mean, right? All the phi, theta, and phi, theta star smaller than epsilon for all theta within the neighborhood of your x star delta, right? There's a definition. We don't need to worry about too much here, okay? But just let you know, it will be useful, okay? So that means what? This is the reason why I'm talking about we need this. Why suddenly we need topology? Why we need linear algebra? Because for multivariable, we need the linear algebra and topology to talk about this. Okay, so that's the idea. And then what? Then after the directional derivative, we have the following two more. Okay, I don't know how to spell, Gatov, okay, something like that. Also a limit. So the difference is, this is what? This is a directional derivative. It's not gradient. Then what about the gradient? Gradient will come from Gatov. So it will be also f, and also something minus something, right? Okay, so it will be x minus plus tv x. So it's the same. If you look back here, it's the same. But then I make it longer. That means actually I will have something. Okay, yes, I will have something. So it will be a linear function. I call it L. L means linear. Okay, L is not the strip constant. This is a matrix. And then this is multiplication. This multiplication is important. I write a O here, and then it will multiply this TV. This TV. Okay. And then we have TV. We have T. Okay, something like this. So what is this? This is called Gatov derivative. Then what about this? There's also another one called Fetcher. Okay. I don't know it's here or here, but anyway. So it will be very similar. Very similar. Okay. But now we do the norm version. Okay. So okay. Equal 0 equals 0. Okay. Why am I talking about this? So first we need to know something. These two things, they have different expression. So in principle, they are not the same thing. But in finite dimension, they are the same thing. Let me tell you, now we have three things. The directional, the Gatov derivative, and the Fetcher derivative. And the relationship, if I remember correctly, the directional is a subset of Gatov derivative, is a subset of Fetcher derivative. That means this one is the most general. Then, and I said, in finite dimension, they are equal. Okay, equal means we are in Rn, okay, they are equal. Then here's a question, very natural question. I'm talking about a thing that are equal, but using free definition. Then you will ask, why am I doing that? The reason why I'm doing that is because now I have free expression telling you the same thing. And now what's the goal? The goal is to compute the gradient, right? Then if I have free expression, that means what? That means sometimes it's very useful to find a gradient using the definition that is easier to compute. So there will be some way calculating the gradient. This is easier, or this is easier, or this is easier. Then we should use the one that's easier. Okay, and now I'm going to tell you the fourth one. Okay, and then of course there are if and only if the what? The classical one. The classical one. That is this one. Okay, is what? This one is. Okay, I should write this. Okay, and this is. Okay, so there are four things. That means we can do the directional derivative, the Gatov derivative, the Fetcher derivative, or the Jacobian. Then, in this sense, that means when you want to find a gradient, you use the one that is the easiest one. You can always do that. And that's the idea. And of course, then later on, you can use what? You can use chain rule, product rule, combine these to make it simple. Okay, later on, I will talk about how do you find the gradient of this ax minus b using these four. We will have a look. Then you will see sometimes using this one is easier for this, or sometimes using this one is easier for this. And then this gives you the idea why we have so many things. And I almost forgot why I write it L. Actually, the L is exactly the gradient. Okay? Okay. So let me go back. This is the big picture. So what's the today? Today is review this linear algebra, topology, calculus, set, differentiation. Why we talk about this? Because we want to do gradient descent. Then to do gradient descent, we need gradient. Then we need to know what is gradient. What gradient is coming from here. But in order to talk about this, we need all these four things. Why? Because this is one dimension. One dimension, we have one-dimensional differentiation, easy. But when we have more than one dimension, this thing, the V1, V2, not necessarily the same. This thing, in this case, is like this is 1, this is 1. But in more than one dimension, this is 3. You can have 2,000, 9,000 here. So we have more than one approach, so we need to talk about linear algebra. And this is the reason why we need all these things. And once we have all these things, we now understand what it is, then we can talk about how do we compute the gradient. We will use directional derivative, Cartesian derivative, Frechet derivative, or Jacobian. And then once you know these 3 or 4 methods, then by definition, now you should know how to find the gradient of this thing. Okay, I made this example yesterday, right? I'm talking about this by using this, okay? And of course, in practice, in the end, you jump to matrix cookbook. But in case the matrix cookbook do not have the expression you want, then you may need to come back here, okay? So now that's the introduction to what we will do today, okay?